We'll be okay. We're going to be okay. Just we're going to do a brief explanation here, brief reasoning behind the fundamental theorem of calculus. The fundamental theorem of calculus really talks about area beneath the curve, right? And I'm going to start bounding this at A. And I'm going to change things just a little bit. Instead of stopping at B, I'm going to stop at X, meaning that we could move that spot. We could move it to the right or we could move it to the left. And I'm going to add one more portion, and we're going to call this spot right here X plus H. I don't know if you ever remember us talking about an X plus H before, but we have, and it was really important for us learning how to find derivatives, okay? So can you tell me what this distance is right here then? This is a distance of H. Everybody agreed? Okay. Have I lost anybody yet? Okay. So I am going to go ahead and I'm not going to use the integral symbol, which, by the way, remember the other day when we did this integral symbol, we said the integral a to b of f of x dx is equal to the limit as what n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. Remember that? Remember that guy? What does this thing mean right here? The sum. And that's actually where the integral symbol came from. When you see this, you think of the letter S, right? So it's like an elongated S. Oh, I'm sorry. In the Greek language, this was definitely an S. I thought we have covered this. So the Greek letter for S, sigma, and capital letter, which came along later. Originally, they didn't have the capital letters. They just did the lowercase letters. So, but anyway, so it comes from kind of an elongated S. That's where the integral symbol comes from. So it means sum. You know, it means adding stuff up. Well, for the sake of, this isn't a true proof. It's just kind of a brief reasoning. So instead of using the integral symbol, I'm just going to use the letter A for area, okay? And I'm going to talk about the area. I'm going to really bound it from x to x plus h, okay? We're going to talk about x to x plus h. So that would be that red area, right? Okay? Everybody okay with that? Would everybody agree that the area from x to x plus h would be the same as the area from A to x plus h minus what? The area from A to x, right? If I take the area from A to x plus h, and I subtract off the area from A to x, I would get the area from x to x plus h. Everybody okay with that statement? All right, you're doing good then. Well, I'm going to look at this piece that I have in red here. Kind of like a rectangle, right? Yeah, with a width of h. What's the height of the rectangle? What would you do to find the height? You'd plug something in and you'd plug it in the function, right? Would you agree that that the height of the rectangle, if I took h times f of x, that I would get approximately the area? Wouldn't be exact, but it would be an approximation. Everybody agree with that? So I'm going to say that if you would take h times the height of the function, that's approximately equal to the area from a to x plus h minus the area from a to x. Interesting. I'm going to divide both sides by h. That means that the function is approximately equal to the area from a to x plus h minus the area from a to x all over h. Now, what if I didn't want those to be approximate? What if I wanted them to be exact? What's going to happen? Like right now, this rectangle is an approximation of that area, but we know that the actual area is a little bit more, right? What could I do to H to make sure that they would be closer together? If H gets smaller, wouldn't you agree that the rectangle would better approximate that area? Yeah. So how do we make something go to 0? We use a limit. So all of a sudden we could say, well, the function is equal to the limit as h goes to 0 of the area from a to x plus h minus the area from a to x all over h. Does that look familiar? Grace says it looks familiar. Could somebody put into words why it looks familiar? That's the derivative formula. You guys remember? Oh. Okay, don't write anything down. I'm going to try to help show you why this is the case. The fact is if I said what is the limit as h goes to 0 of sine of x plus h minus sine of x all over h. If I asked you to compute that, does anybody know what we would get? We would get cosine of x. This is how you originally found a derivative. Watch, we'll carry you through one example, and hopefully that will really help you out as we move forward. This is my last chance to try to convince you of this situation if you don't recognize it so far. I'm going to take a function. F of x is equal to x squared. Can somebody tell me what the derivative is? Now, the fact is that you know that the derivative is 2x because you're able to use a shortcut rule. Well, there was a time where we weren't able to do that. What we had to do instead is we did the limit as h goes to 0 of x plus h quantity squared minus x squared all over h, right? And we know that you're going to get 2x from this because this is the function, x squared. This sits right where the function is, and the derivative of x squared is 2x. Now, if you don't believe me, let's work it out. The limit as h goes to 0 of, what does this become? X squared plus 2xh plus h squared minus x squared all over h. What happens? The x squareds cancel. And can you divide an h out? So I have the limit as h goes to 0 of, when I divide the h out, I get 2x plus h. So if we plug in 0 for h, what are we left with? 2x. So you can see that this thing ends up being 2x because the derivative of x squared is 2x. Look, we know what this ends up being because the derivative of sine of x is cosine of x. And to make the connection, hopefully in a way that you understand, we know then that the derivative of the area function is the function. Oh my gosh, what does that mean? Here's what it means. The area function, the whole thing we've been trying to figure out this whole time, if you were to take the derivative of the area function, you get this function up above. So we need to make two statements. Statement about f of x. F of x is the derivative of the area function. Well, wait a minute. What we're trying to do is not go from the area function to the function. We're trying to go from the function to the area function. So what that means is this. What about the area function? The area function is the antiderivative of the function. Yeah. Well, that's pretty cool. What does antiderivative mean? Oh my goodness. We better think about that. Before we do this, flip over to this part so we can think about it. Do you know what the antiderivative of x cubed is? You got to think about what would you take the derivative of to get x cubed? Did you say? 4x to the fourth? Excellent idea. 4x to the fourth. Now, let's try. Take the derivative of that. Do you get x cubed? You end up with 16x cubed. So it was close. So instead of multiplying by 4, we should really have a, yeah, it would really be if we had x to the fourth over 4, right? So if we take the derivative, we would get 4x to the third over 4, which just gives you x cubed, right? So the antiderivative of x cubed is x to the fourth over 4. Let's see here. What did you do to the exponent? You raise it by 1, right? And like when we take a derivative, we usually multiply the exponent out in front, right? But now we should divide. So what we do is we raise the exponent by 1 to get x to the fifth. So we got 5x to the fifth, and we divide by our new exponent. What does that simplify to? X to the fifth. Is the derivative of x to the fifth equal to 5x to the fourth? Yeah, it is. Let's try this. You raise the exponent by 1 to get 4x to the 7th, and then you divide by the new exponent, which is 7. So that's the antiderivative of that. So we increase the exponent by 1, and we divide. Okay? Let's try one more. This one's complicated because I got something in the denominator, right? This is 3 over 2x to the negative 3, right? So I'll take 3 over 2x to the, I increase it by 1, that makes it negative 2, and then I divide by that negative 2. Anybody know what 3 halves divided by negative 2 is? Negative 3/4. And we drop the x squared to the denominator. So negative 3 over 4x squared is the antiderivative of 3 over 2x cubed. Let's try it. Let's try it. Okay. So take your time with it. Okay. And this is a lot of what we're going to take time with today is taking the antiderivative. Okay. We're not going to just gloss over it. We're going to take time with it. So what we do is we take this we take the exponent and we increase it by 1, and whatever that new exponent is, we divide. So watch what happens. You can always check your answer by taking the derivative. What's the derivative of x to the fourth? Well, it's 4x to the third, and I have it divided by 4. Those cancel, and I get the x to the third. The next one, look at this. So we took the 5x to the fourth, and what we do is we increase the exponent by 1 to get 5, and we divide by that new exponent. So you get x to the fifth. That's your antiderivative. Well, let's try taking the derivative of it. The derivative of x to the fifth, drop the exponent in front, 5x, and decrease the exponent by 1, and you get that. So you can always go back and forth to check to see if you get it. Okay? So, sorry to have you flip back, but flip back here. And the fundamental theorem of calculus, part 1, this is something that we have to talk about in a couple days. We're not actually ready to talk about part 1. I know it seems ridiculous that you would not learn part 1 first, but for whatever reason, I can't find a calculus textbook where it's really different. We always talk about the fundamental theorem of calculus part 2 first. We'll get to part 1 later. But the antiderivative for f of x equals x to the nth is this. We call the antiderivative big F. Big F. And now be equal to x to the n, n plus 1, divided by n plus 1. So let's make sure that we're all clear here about our notation. If f of x is my function, and it is x to the nth, How did we show that something's the derivative? What do we do to that? We show prime. F prime of x. And what was the rule then if we take the derivative? Yep, we decrease by 1, and we put the exponent out front, right? That was how we took derivatives. If you do an antiderivative, we call that big F. And it's x to the n plus 1 over n plus 1. So those we have to kind of keep straight. And that's part of what makes calculus 2 challenging, is you don't just take derivatives, you also take antiderivatives. You have to keep it straight which one you're doing sometimes, okay? Right now, we're going to spend a lot of time focusing on just antiderivatives, okay? So you guys have a big question about, what the heck does this have to do with area? And here's the idea. Fundamental Theorem of Calculus Part 2 says this. The integral from a to b of f of x dx. We just got done doing that. You guys did your assignment yesterday, okay? Mr. Crafter told me that yesterday during his study hall, he finished off all 8 problems, right? Atta boy, okay? Did you guys do all those? Maybe, maybe not. Rebecca's like, I have no idea what's going on. I have mono. We're glad you're here, okay? But you get to see the shortcut right now. The integral from a to b of f of x dx, I don't have to add up the area of an infinite number of rectangles. Here's all I have to do. I find an antiderivative f, and I plug in b. Minus that antiderivative with a plugged in. And that's it. So we write where f is any antiderivative of f. So keep a finger in your notes there, and I want you to go to this page right here, the one that says, yeah, this guy right here. We looked at the area beneath the curve from x squared from 0 to 2. So what that meant is we looked at the parabola from 0 to 2 and we found that area. Look at your work that you did. Wasn't it cool? You see all the summations, and you see all those formulas you plugged in. What did you come up with for an answer, folks? You came up with 8/3, right? You came up with 8 over 3. All right? We're going to do the same problem, but we're going to do it using this shortcut piece, the Fundamental Theorem of Calculus Part 2. Let's try it. It says evaluate the following, the integral from 0 to 2 of x squared dx. It's the same thing that I just showed you that we did a few days ago. But now what we're going to do is we find an antiderivative. What's the antiderivative of x squared? Increase the exponent by 1 and then divide by that new exponent. And then here's the notation we write. We write this bar, and it means we're going to evaluate it at 2, and we're going to evaluate it at 0, and we'll subtract. So I'm going to plug in 2. What is 2 to the third? Over 3. Minus, now I'll plug in 0. What's 0 to the third? 0 over 3. What's 8 over 3 minus 0 over 3? And that's the exact area. Yeah. Isn't that incredible? You guys, you're going to want to use this instead of doing the work that you were doing the past couple days. You need to do that work. You're going to be asked to do that on a test. If you want to verify your answer by checking it this way, go ahead, all you want. But you have to still do that original work, because that's part of the calculus. I'm sorry. I didn't force you to take the course. You made a choice, and you're going to be better off because of it. Push-ups for your brain. All right, here we go. Now I have the area from 2 to 4 of 3x squared dx. Always good to think of the region that you're working with. What is the what does the shape 3x squared look like? A parabola, and you're going from 2 to 4. So it's this region right here that you're looking to find the area of. Is it could be positive or negative? Positive because it sits above the x-axis. We talked about area being positive or negative a little bit. So what I do in order to evaluate this is I take the antiderivative of 3x squared. What's the antiderivative of 3x squared? Yeah, if you take, so you go 3x to the third over 3, right? Which is just, so I take x cubed and I evaluate it at 4 and 2. $64 minus 8 is 56. Look at that. Is that amazing? I don't see enough smiles. Okay, you're right. We'll just go back to doing it the old way from now on. What? So I'm looking for the antiderivative of 3x squared. So I take the exponent and I increase it by 1, and I divide by that new exponent. So I get x cubed, I plug in 4. 4 cubed is 64, minus 2 cubed is 8. Yep. Okay. All right. Let's get a little bit more complicated. We got the area from 1 to 2 of 3 roots of x. Do you know what the graph of 3 roots of x looks like? Looks like that. We're going from 1 to 2, so we're looking at this area right here. Positive or negative? Positive, yeah. So we're going to check that guy out, see what we get. This is 3x to the 1/2. So if I increase the exponent by 1, I get 3/2, and I have to divide by 3/2. Yeah, so dividing by 3/2 is the same as multiplying by 2/3, and the 3's will cancel, won't they? So I end up with 2x to the 3/2, and I'm going to evaluate that at 2 and at 1. Let's plug in 2. What's 2 cubed? 8. Square root of 8. Can I simplify that? 2 roots of 2 times 2. So I get 4 roots of 2. And then I plug in 1. 1 cubed. 1. Square root is 1 times 2 is 2. So 4 roots of 2 minus 2 is the exact area found underneath the curve at that spot. Thank you for asking. I was feeling tempted to do this, but didn't know if anybody else was there with me. It's nice to know somebody else is. Second, calculate number 7. There is my curve. I'm going to go from 1 to 2. 3.6568. And if I would take 4 roots of 2 and subtract 2, look at what I get. Just a couple more examples, and you'll be ready to try this on your own. Oh, no. Look at that. There's a lot of stuff going on there, isn't there? In fact, I'm going to try to get a feel for what the area looks like ahead of time. I'm going to type this into my graph. X cubed minus x squared plus 2x minus 3. Is it above or below the x-axis? It's below, isn't it? So should it be a positive or negative area? It should be negative. So it's always important to think about that graph and what that area is going to look like. Doesn't have to be a super, impressive graph, but it needs to be something. So what's the antiderivative of x cubed? X to the what? 4th over 4. Minus x to the 3rd over 3. Plus x squared. Gigi has got it. Minus 3x. I evaluate 1 and 0. If I plug in 0, what am I going to get? 0. So we can really just plug in the 1. And it looks like I have fourths and thirds, so I'm going to write it as twelfths. How's that? So if I plug in 1, I get a fourth, which is 3/12 minus 4/12 plus 12/12 minus 36/12. And I get, let's see, 3 minus 4 is -1, plus 12 is 11, and 11 minus 36. Sure enough, if I calculate the integral number 7, and I go from 0 to 1, that should be, let's see, -2.083. There it is. Cool. 2 more. We'll let you go. Oh, no. What's the antiderivative of sine? Very nice. Alex, you were so confident. You said negative cosine. Why are you so confident about that? Because you just know it. What if we don't know it? What do we do? If you think about it, if you said cosine, well, what's the derivative of cosine? Negative sine. So Alex said negative cosine. The derivative of negative cosine of x is going to be positive sine. That type of thinking is going to have to start to come true for you. I evaluate at pi and at 0. Let's think about the sine graph so we can have a little appreciation. Where does sine start? So it's at the middle, and it goes like that, right? And this spot right here is pi. So we're looking at that area right there. So we should get a positive value. I'm going to plug in pi. Look at this spot right there. The terminal point is -1, 0. So what is, D. Weiland, the cosine of pi? Times negative, be positive 1. Minus, now I have the cosine of 0, which most people will say 0. But as you look at 0, it is the coordinate 1, 0. So let's see what we get. The cosine of 0 is 1. Make it negative. So I have 1 plus 1 is 2. Do you remember us doing that problem? We did 200 rectangles earlier, and we used our calculator. Comes out to be exactly 2. We did it that quickly. Yes. Come on in, sir. How are we doing? What can I do for you? Oh, no, it's okay. It's okay. We're not really doing anything important today. Now, she's a part-time student. Yep, and he definitely doesn't belong. He's not in this class anymore. Let's see. He's here. I think we're good to go for the rest of you guys. Yep. Yep. Well, they lost their chance, I guess. Sorry, YouTube. We got a little interruption here. People are flocking to get into calculus class whenever they can. Just got a yawn from Gigi. Apparently she was up early feeding the chickens. Whoop. Oh. Chris, Zeno, Drano. Okay, you might choose to write this down somewhere. We have sine of x, we have cosine of x, we have negative sine of x, and we have negative cosine of x. So Grace had a good question, you know, how we find out the antiderivatives of some of these trigonometric functions. This is the best way to do it, in my opinion, okay? And so we start listing the function. What's the derivative of sine of x? Cosine of x. What is the derivative of cosine? Negative sine. What's the derivative of negative sine? Negative cosine. And what is the derivative of negative cosine? Positive sine of x. So what does this mean? This tells us everything we need to know right here, okay? If you're wondering the antiderivative of sine, you don't look here, you look here. The antiderivative of sine is negative cosine. The derivative of sine is positive cosine, okay? The derivative of cosine, negative sine. The antiderivative of cosine, positive sine. This is how you go back and forth. Everybody see it? If you'd like to do the extra work and make this big f of x over here, you end up just using this chart. The antiderivative of sine, well, we look right there. It's negative cosine of x. The antiderivative of cosine, let's see, it's right here. It's sine of x. And, yep, we broke it. It's done. So, you get the idea? That's how you can work through that. We have one more problem. You guys are ready for your worksheet. Ooh, you said packet. Challenge accepted. We're feeling a packet. Yeah. Sine. The antiderivative of negative sine, I find negative sine, it's positive cosine. The antiderivative of negative cosine, I find negative cosine, it's negative sine. Does that help? Yep, there you go. Okay, our last problem. Let's wind down here. Wind down Wednesday. Optional Tuesday. Terrific Thursday. No school Friday. All right. Integral 1 to 5 of 2 over x squared. This raises a really, really important point for us to look at. Do you know what the graph of 1 over x or 1 over x squared looks like? It looks like that, doesn't it? If the function is discontinuous, the fundamental theorem of calculus does not apply. But is this function discontinuous from 1 to 5? No. Okay. If it was negative 1 to 5, you would simply write does not apply. Does not apply. Very good. Yep. So I have 2x to the negative 2. I need to find an antiderivative for 2x to the negative 2. 2x to the negative 1 over negative 1, which is just, isn't that just negative 2 over x? So I evaluate that at what two numbers? 5 and 1. Plug in 5. What do you get? Negative 2/5 minus, plug in 1. What do you get? Negative 2. So plus 2 or plus 10 over 5, which would be 8/5. Folks, that's the fundamental theorem of calculus part 2. It makes finding the area bound underneath the curve extremely simple. I can't make it any easier than that, okay? The area that you did yesterday and the day before, still important to do. You got to be able to do it. Normally, I'd be giving you a day to work on that assignment today, but seeing how we are, let's see, 6, 7 days behind, we we can't take too many days like that. No, it isn't your fault. Well, I'm not punishing you. I'm just not taking it as easy on you as I have past years.